Hello, my name is Gaby Mayorga Adame. I'm an oceanographer from Mexico, but I work for the UK National Oceanography Center. And my main interest is the interactions between physics and biology in the ocean. And I am working in the Marine System Modeling Group. And the aim of our group is to develop state of the art models and use them to better understand and predict how the ocean works and to address fundamental societal changes. I volunteer for Climate Match to put together the ocean acidification project that you will be working on. And Lidia Krinova is a marine biologist and data scientist that jumped on board to help me with the impact questions, particularly to locate some data and online tools that you can use to put these questions into context. And there's my website if you like to check out some of my projects. And these are the intro slides for the ocean acidification project. However, I found this amazing video by Noah that explains it all. So I'm just going to go ahead and play that for you.
Marine pteropods, or sea butterflies, are found throughout the ocean and are a major food source for fish and other organisms. In laboratory experiments, this pteropod shell dissolved over the course of 45 days in seawater adjusted to an ocean chemistry projected for the year 2100. What changes in the ocean might be putting pteropods at risk? The burning of fossil fuels has caused levels of carbon dioxide in the atmosphere to rise. This carbon dioxide, or CO2, doesn't just stay in the atmosphere. Roughly 30% of it is absorbed by the ocean. When CO2 reacts with water, it forms carbonic acid, which quickly releases a hydrogen ion, or H+. The more hydrogen ions, the lower the pH, or more acidic a solution is. As CO2 levels increase over time, seawater will progress towards the acidic end of the pH scale, a process called ocean acidification. We can make projections of this change in the ocean pH over time. It is expected that later this century, if CO2 emissions continue at the current rate, the average pH of the ocean will drop from 8.2 to 7.8. This relatively small decrease in pH may not seem significant, but it could impact many species of marine life. For pteropods, corals, and other species that depend on shells and exoskeletons, ocean acidification will lead to a decreased availability of dissolved calcium and carbonate, the chemical building blocks they use to make their shells and skeletons. If ocean chemistry changes as expected, shells with calcium carbonate mineral structures may begin to dissolve, depending on where they live in the ocean. How do we know that ocean acidification is happening? Scientists at NOAA and across the world have measured these chemical changes over the past 40 years during research cruises, taking hundreds of thousands of ocean water samples. Shown here are the results from cruises in 1991 and 2005, where the availability of the shell mineral was sampled. In both years, the highest concentration of available shell minerals were found in the surface waters as shown by the dark yellow colors. Deeper waters naturally have very low availability of these minerals. However, when we look at how these values have changed between 1991 and 2005, we see that the availability of the shell mineral decreased much more in the surface waters, as indicated by the blue colors. In other words, ocean acidification is impacting shallower areas much more than deep areas. Shallow waters are where the bulk of the ocean productivity occurs, including the most diverse and economically important species and habitats. And these changes aren't occurring in just certain parts of the ocean. They're occurring throughout the entire ocean. Today, repeated research cruises and permanent sampling stations continue to monitor changes in pH and availability of calcium carbonate minerals. As the ocean approaches a critical transition between shell building and shell dissolving, food webs in the world's oceans could be impacted. Phytoplankton and zooplankton, like pteropods, form the basis of most oceanic food chains. Coral reefs form the foundations of the most diverse marine habitats, and shellfish, such as oysters and crabs, and finfish, such as salmon, support economically important fisheries in many of the world's coastal communities. People depend on the viability of these species to ensure a healthy future of our own.
So that's a great introduction for the ocean acidification project. Okay, so that was a great introduction for the ocean acidification project. And now I'm just gonna go on with the slides really quickly. Yeah. So there we are. Just as a recap, so the ocean is absorbing around 30% of the atmospheric CO2. And this is making the ocean more acidic. This absorption is not uniform throughout the ocean. There are places where the ocean is absorbing CO2, and there is places where the ocean is degassing CO2 back into the atmosphere. And this depends on the difference in the concentration at the ocean-atmosphere interface. It happens both on land and in the ocean. But in the ocean, it's due to the production and consumption of CO2. So the consumption is due to phytoplankton photosynthesis. And then the production of CO2 is due to the respiration of organic matter or the decomposition. So some places absorb CO2 in the ocean, some places release CO2 into the atmosphere. But this 30% is just the global average. And by absorbing this amount of CO2, the ocean is becoming acidic. And it's already changed by 0.1 pH units. And this seems like a very little change. However, we need to remember that the pH scale is logarithmic. So this equates to around 30% more acidity. And this is a problem for most marine organisms. Of course, it is more of a problem for those creating calcium carbonate shells. So this is a bit of the chemistry, just also in the video. So when CO2 is absorbed into the water, hydrogen ions get released. As a CO2 is dissolved into water, some of it remains as a CO2 dissolved. And then it also generates other ionic and non-ionic chemical species. As we can see here, we get carbonic acid, this guy here, and then we get the bicarbonate ion. So ion is charged molecules, either with a positive or negative charge. And then we get also the carbonate ion. So as we saw in the video, two things are happening. One is the acidity of the water is increasing, and then the availability of this carbonate calcium that is used to generate the shells of a lot of marine species, both plankton and other sessile species like shells, mussels, and corals. So it is decreased the availability of this mineral required for them to build their shells. So it's like two pieces of the same problem. So the ratio of these chemical species varies according to this graph based on pH. You will get different concentrations of each of them. And it also depends on seawater temperature, pressure, and salinity. So ocean acidification is basically a very big problem for marine calcifiers, all those organisms that use calcium carbonate to build their skeletal structure. And this is so big and so bad of a problem that it's called the other CO2 problem, or the twin evil of global warming. Further impacts for the marine ecosystems due to climate change include the increase in temperature and the loss of oxygen. So these three things, acidification, increased temperature, and the loss of oxygen, it's called the deadly trio of climate change. And it's exerting extreme pressure into the marine ecosystem. Of course, it varies in space and time, and the most affected organisms, as I say, is calcifiers. But even fish, they have some calcium carbonate structures like the otoliths that control their sense of equilibrium into the water. And it's been shown that ocean acidification also affects the development of larval fish and also their behavior, particularly their capability to escape from predators. So it is likely that this ocean acidification issue is having impact in most marine organisms and therefore all the ecological services that they provide. And therefore they end up affecting coastal communities through the income from tourism, fisheries, aquaculture, and their food availability. So this is just a picture of different planktonic foraminifera. So these are tiny zooplankton creatures that have calcium carbonate cells. They are so tiny that they just float in the ocean. And as this, there is many different calcifying species, although we just usually think of the most popular, like corals and shellfish. And as for the data we will be using for the project is reanalysis data. Reanalysis data, it's a combination of model data and observations, and they are put together through this data assimilation process that is an optimization of the both data sets to get like the best available product. And it's this same methodology that is used for forecasting. Like for the weather forecast, you have an atmospheric model or a couple ocean atmospheric model that gives you a prediction. And then to that result, you can assimilate periodically observations as they are gathered. So reanalysis data, it's very similar to this. However, it's for longer time spans. So you assimilate data of the last decade into a model data set, and you get this best estimate of whatever. So in our case, we are going to be using the variables of pH and then CO2 and sea surface temperature. And they come from two different sources. One is from NOAA and one is from the Copernicus dataset from ECMWF, that it's a European product. They are both global datasets. They are gridded, so across the globe, so you get a uniform latitude longitude grid with the data on it. And they have different time spans, but they go from pre-industrial times to the present or some prediction up to 2100. So it is mainly these two datasets that we will be using. And then there are, as I mentioned, the online tools that Lidia kindly provided. And with those, you can explore the species distribution of many species across the globe, and also the economic value of some of these marine species or their ecosystem services like aquaculture, tourism, get an idea of the economical impact that ocean acidification can have in different regions of the coastal ocean. So I hope you enjoy the project. The data you will be working with is in NetCDF format. So this is a format that scientists use to try to unify how we publish datasets. It is in binary format, so you definitely need something to read it. Python does it great. And it has some standard metadata. And it's really easy to load the data and see the data structure. And you will have guidance from a notebook and your project CA on how to work. I hope you enjoy working this project, and thank you.